So I will officially welcome everybody. Good mid-afternoon and welcome to the final mid-afternoon masterclass for this year's Science Festival, brought to you by the University of Melbourne as part of National Science Week. I'd like to start by acknowledging the Kulin Nations as sovereign custodians of the lands on which the University of Melbourne campus is situated, and where the mid-afternoon masterclass team and many of you, our audience, are zooming in from today, of the Wurundjeri, Boonwurrung, Yorta Yorta and Dja Dja Wurrung peoples. We extend our respects to ancestors and elders past, present and emerging, and to all First Nations people, including those who may be in the audience today. Welcome. So I am Julia and I will be your host today as we bring you a brilliant scientist from the university and also some industry representatives as well to discuss mapping the geology of Melbourne. So without further ado, I'll welcome all three of them to the event, as you can see them on screen already. So first to Mark Quigley, Associate Professor of Earthquake Science in the School of Earth Sciences here at the university. He's a teaching and research academic and senior academic advisor in the Faculty of Science. So Mark has undertaken geological research on all of Earth's continents, published more than 100 research articles, and advises the United Nations Office of Disaster Risk Reduction. He is a fellow of the Geological Society of America and recipient of the GSA Public Service Award and New Zealand Prime Minister's Science Communication Prize. He's a proud husband, father of 2 toddlers and a Roodledore, sports enthusiast, gardener and resident upon the basaltic lands of the Wurundjeri Willem people near Mary Mary Creek. Welcome, Mark. How are you today?
Hi, thank you for the intro. I'm very well.
Fantastic. All right, very good. Well, I'll keep going along. Now, we do have 2 Michaels in the panel today, so I do hope that's not going to confuse everyone or confuse myself and everyone when we do the Q&A, but we'll see how we go. So Michael number 1, Michael Webster is a senior engineering geologist working for Golder Associates in Melbourne. He has worked on a variety of projects across Australia, including the Melbourne Metro Rail Tunnel, Sydney's WestConnex road tunnels, and the Australia 108 skyscraper in Melbourne. Like Mark, Michael is a proud father, husband, and avid gardener. Welcome, Michael number 1.
Thank you very much.
Fantastic. And Michael number 2, Michael Heath, recently completed a PhD in geology at Melbourne University, where he mapped out the young lava flows of the Melbourne area. He now works at Golder Associates, where they solve the world's environmental and geotechnical problems. Using 3D modelling and geospatial software, he helps provide a fresh perspective on a wide range of issues, from mapping contamination plumes in groundwater to visualising how subsurface geology interacts with major infrastructure. Fascinating stuff. Michael is a father of 1 2-year-old, a keen cyclist, a sportsman in normal times, and is most at home in the field somewhere, separating a piece of basalt from itself by way of extreme force and sledgehammer. I love it. Welcome, Michael. How are you going?
Great, thanks. Thank you for the kind words. Let me say I didn't know this was going to get read out live, but yeah.
Okay, there you go. Well, look, it's very important that everyone knows who you are and what this event is going to be all about. So. Yep. In a moment, I will be throwing to our speakers, to Mark and Michael Squared. So they will be discussing how the earth under the city of Melbourne was shaped and how this impacts development today.
Well, good afternoon, virtual humans, and thank you for your company this afternoon. It's my great pleasure to be able to speak to you via my computer and with 2 colleagues from Golder Engineering. The masterclass today is about mapping the geology of Melbourne, but it is going to start with a broader view of what geological mapping actually is. And so just to kick us off, I should say that geological mapping is a science, of course, of hypothesis testing and refinement and digging holes and learning things. It is a visual art. It is a way of communicating through the visual media, and it is also a humanities subject. It is something that sheds light on who we are and how we came to be, and it surrounds us everywhere. And once you begin to make geological maps, you see the world in a very different way and you can never go back. And so hopefully today you'll be able to get a window into the sort of view that some of us have of the world and the role of geological mapping in that. In Melbourne, our rocks and soils offer us windows into things such as the assembly of ancient continents, of mountain belts, ancient mountains, and our mineral resources, as shown here by a road cutting in our Silurian sedimentary rocks of Greensboro. It offers us opportunities to learn about ancient life and environments. Here are some graptolites from 440 million years ago in the Melbourne rocks. It offers us ways of connecting culturally to our indigenous peoples, better understanding their landscapes and how geology, what the geology was like at the time that the indigenous roamed these lands. And it offers us very much in the sense of informing decision-making for hazards, for infrastructure and sustainability. And I should say, when we live in a city of 5 million people with its infrastructure and busyness, at least at most of the time, it's a little bit easy to get disconnected from the natural environment. But the thing is that geology, it impacts us in all of these decisions all the time. And my guests will certainly offer a perspective of just how much it does so in their talks today. I want to start off with what a lot of people perceive when they think of geological maps and the birth of geological maps. This is a very famous geological map by William Smith in 1850, a delineation of the strata of England and Wales with parts of Scotland. You can see essentially this is a depiction of the different rocks and soils through lines, boundaries drawn, beautiful color shading, both in a map view and in a cross-section view. It gives us a window into geological time, the thicknesses of different strata, and so on. In a sense, it is a pictorial view of Earth history. And I want to try to convince you that a geological map, it's this visual depiction of the spatial distribution of Earth materials and structures. It can be in one dimension, as in just the map view, and it can have 2 dimensions, cross sections. It can be 3 dimensions by some of the models that you're going to see shortly. And it can be 4 dimensions by implementing an element of time and looking how our geology changes through time. It's important to realize that geological maps are models with adaptive capacity, meaning they can be constantly refined and changed across a variety of scales. They have a myriad of uses and users for different purposes. And there are a variety of ways in which we might communicate about geological maps, and this is certainly one way. Of course, one could very well argue that there were geologic mapping going on much before this. The Turin Papyrus map, some 3,000 years ago, made by the ancient Egyptians, depicted the distribution of different rock types, different soils, different minerals in the rocks, locations of copper to make tools and for value, lithologic variations in the Wadi gravels, which were used, for example, to source water, to make concrete aggregate, and also information on quarrying and mining, including gold. So we were making geological maps. We, the royal we, were making geological maps 3,000 years ago. One of the more famous versions of geological mapping is from 1556, De Re Metallica, by Georgius Agricola of Saxony. And I just love this geological sketch shown here on the left of cross-cutting veins, because we do the same sort of thing with geology students today. And the description that I'd like to read out for you in terms of why it's important to make this particular type of diagram. The best veins in depth are those which run from the 6th or the 7th direction to the east, or the 6th or the 7th to the west, through a mountainous slope, which inclines to the north, and whose hanging walls are in the south, and whose foot walls are in the north. A beautiful example of geological mapping through time. But I would argue that the first geological mappers are our indigenous peoples. I think that Aboriginal songlines, the detailed maps through these physical and spiritual worlds, were communicated over thousands of kilometers and over tens of thousands of years. And in the rock art and in the engravings, some of these ancient engravings, one can see graphical depictions of place, of water holes, of pathways that are in themselves controlled by geological features. And so I think that we can make the case that some of the first geological mappers are Indigenous peoples of Australia, and that's quite a nice learning from which we can build upon. In Melbourne, the first geological map was made by Alfred Selwyn from the Geological Society of a Survey of Victoria in 1856. I love this map because it is just so old. It was made by Selwyn, one assistant, and a tent keeper who mapped more than 2,500 kilometers squared every year over a sustained period of time. And so I can use this when my geology undergrads complain about a 10-kilometer traverse as an example of just how geological mapping can be done. You can see the depiction of different granite units and igneous intrusive and extrusive rocks, which now form our Dandenong Ranges. You can see the Silurian rocks throughout Melbourne, basaltic rocks and so on, with lots of sketch notes made on this geological map. It's something of real value. And we have now come to understand that with the time that our Silurian rocks were being deposited, well, before that, Australia was part of a supercontinent called Gondwana, with a subduction zone in the Paleo-Pacific Ocean. We were connected with Antarctica. And it was a very interesting geological period of time. At the time that our rocks, the Silurian rocks, were actually being deposited, the Earth reconstruction looks something like this. You can see Australia just off on the right side of this diagram is connected with part of this Gondwanan supercontinent. And so, as I say, we are still standing on the shoulders of giants. We take students out into the field, we give them maps, we ask them to draw contacts and make notes on them, just as our forefathers did long before. And of course, we do different things. We may drape these geological maps like this one from my colleague Brendan over topography, but the premise is just the same. In the 1858, we began to make quarter sheet maps of Melbourne's geology. This built on field topographic surveys. The scientists at the time dug pits. They looked at road cuttings. They scrambled in creeks and rivers, and there was a major focus on understanding where we could, the resources were to make bricks, to make gravel, to find gold, and so on. Here's a beautiful example of that map in the Studley Park area, where we still take students today, showing these deposits, the yellow colored units of quartz and ironstone gravels overlaying these Silurian rocks. And I can tell you that in the modern context, we can visit these locations with our Microsoft Surfaces and our iPhones, with apps that show us Melbourne's geology and allow us to pinpoint our location accurately. We can scramble along on the cliffs and look at those rocks and find those exact types of materials that were being looked at in the 1850s when these maps were being drawn. And of course, just like the holes dug in yards in 1850 to understand what geology is, when we plant trees on our own properties, we can still do the same thing. This is a cubic meter hole I dug in my front yard. About halfway through, I realized I was hitting a solid basaltic rock over in Brunswick. And so again, it gives us an opportunity of what lies beneath. Here's an example of a geological map from the Geological Survey of Victoria in 1880, providing just an example of how diverse Victoria's geology is, gold and coal and so on. The 1937 map by the Department of Mines, Victoria. Again, getting an enriched understanding of Melbourne's geology. The Geological Survey of Victoria 1959 map, showing now folding and faulting, and this was occurring in the context of major breakthroughs being made in our understanding of plate tectonics. And so folds were being recognized in Melbourne's rocks and Silurian sediments. Deep leads, these ancient buried river channels running through Melbourne, some of which were gold bearing, were being recognized. They're shown here by these red lines here beneath the basalt. And a better refinement of the age control in terms of the relative chronology of deposition of different units and so on. And so the geological map, this is Collingwood in the middle here, Fitzroy and so on. The geological maps are becoming more sophisticated in a lot of ways, with more units being recognized, more structure being recognized and so on. And of course, with the understanding of plate tectonics, it allowed us to better understand what was occurring in this region on the sort of plate scale. And at that time, at 40 million years ago, which is recorded in some of the sediments of the region, Australia was beginning to break away from Antarctica and break away from New Zealand and basically become the continent that it is today. The Geological Survey Victoria 1974 map, again, refined contacts. You're seeing it becoming a lot more detailed, subdividing different units and so on. In a sense, this was our geologic map, our gateway into the three-dimensional maps of today, showing these thick quaternary river alluvium sediments along the Yarra here, these Miocene gravels, the quaternary lava flows that Michael will be discussing very soon, and the gray colored Silurian rocks with the folds and faults of Melbourne. And this is an example of a geological cross-section through those folded Silurian rocks there, showing the same sort of things that you can see when you drive along the Eastern Freeway, the folds and the faults in those rocks. So we now, with time, we have access to more data. So we are able to not only map geology at the surface, but map it at the subsurface. We're able to stitch it together seamlessly across multiple map sheets, use information like the magnetic signature of the Earth, gravity data, and so on, to really reconstruct the structure, the lithology of Melbourne's rocks. And we bring in a whole bunch of other tools, geophysical tools like seismic velocities and so on, to paint this more sophisticated picture. And before I turn it over, I'm going to leave with you a couple beautiful images here of the sort of things that we're working on at the moment. This is in southwest Melbourne. The You-Yangs are the large mountain that you can see in the middle of the image there. You can see these linear scarps running through this landscape here. We are quite confident that these things are telling us about youthful, large surface rupturing earthquakes in this landscape that pose both a shaking and a fault rupture hazard to Melbourne in its area. And we're using this kind of high quality data while still standing on the shoulders of giants to enrich our understanding of our seismic hazardscape. And here on the opposite side of the bay in the Beaumaris area is an example of some of Melbourne's topography, showing an uplifted area to the northwest and a downdropped area to the southeast that we think coincides with something called the Beaumaris monocline. It is a structure that we think has the potential to host earthquakes, has deformed quaternary sediments, young sediments, and is something that is of real value and interest of us as we continue to learn more about the geology beneath our feet. I'm going to now turn over to Michael Heath, and I will rejoin you again shortly. Thank you for your company.
So I'm going to talk a little bit about the volcanic history of the Melbourne area. I've just recently completed a PhD project looking at the lava flows of the Melbourne area. So trying to map all the different lava flows and also date the lava flows in the Melbourne area. So starting with a wider view, Melbourne is part of what's known as the Newer Volcanic Province. This is the most recent expression of volcanism in southeastern Australia. You can see on the map here that it covers quite a large portion of the surface in Victoria, a little bit in South Australia, and there are at least 416 eruption centres. So each of these dots on the map here is one eruption centre. The highest concentration of them is up in the Central Highlands area, so up to the west/northwest of Melbourne. But we're going to concentrate on the Melbourne area for the rest of this talk. So for my project, I wanted to try to map out all the different lava flows. So from the geological maps, we had a pretty good idea of where the lava was and where it wasn't. But I wanted to try to map the flows basically from their eruption points to wherever they terminated, and then also to be able to date the flows and in that way be able to tell more of a concise volcanic history of the Melbourne area. So the way I went about mapping the lava flows was starting with field relationships. So collecting a lot of samples out in the field. I collected about 700 samples from across the Melbourne area. And in the field, I was looking at things like geomorphology and stratigraphic relationships. But in general, this wasn't very good at telling the difference between different lava flows. So basically all basalts in the field look the same. You might be able to tell by age in some cases, but you never really got to see multiple lava flows together in the field. And so in cases like this, where you might think that there's, it might look like there's a younger flow sitting above an older flow, in reality, what you have is the same eruption event and maybe an upper flow unit and a lower flow unit, but basically the difference is just the buildup of the regolith profile, so alteration over time, turning it into a bit of a soil on top. So yeah, field relationships weren't that great for telling the difference between different flows, but some of the techniques that I used that were a bit more effective included petrography, so that is looking at the flows under a microscope. Some of the lava flows were quite different texturally and also mineralogically, so they had different minerals, and so in the case of flow A and B here, you can see they look quite different under the microscope. Geochemistry was good for some flows, particularly when you had larger volume flows and smaller volume flows. So flow A is an example of a larger volume flow, which has high silica, lower alkali content. And the smaller volume flows tended to have lower silica, higher alkali. So it was pretty easy to tell the difference between those. In a lot of cases though, the only way to be sure was actually dating samples. So I used the argon-argon dating method, and you could definitely tell whether a sample belonged to flow A at 0.8 million years or flow B at 4.5 million years old. So after using all these various methods to try to map out the lava flows, I can now kind of tell a bit of a story of the volcanic history of the Melbourne area. So that's what I'm going to go through for the rest of my part. So over on the right, we have an aerial image. We're starting at 8 million years ago. And as we move forward in time, you're going to see the lava flows appearing, and the cross section from east to west through here, beginning again at 8 million years ago. So at this time, it's a fairly ancient surface. Some of the youngest stuff we have around is the Bulla granodiorite, about 390 million years old. And we have these wide and deep valley systems, particularly over in the east of the Melbourne area. And they'd had a long time to form. So between about 8 million years and 4.6 million years ago is when the activity starts, or the recent activity begins. And we have these 4 small volume eruptions. None of them interfere with the cross section, so that doesn't change at this stage. And we're not sure whether these 4 should really be considered part of the newer volcanic province or not, as they're quite different geochemically. But the real start of the newer volcanic province was around 4.6 million years ago. And there were 3 eruptions between 4.6 and 4.5 million years ago. The first one at Mount Ridley, well, around the same time from Mount Ridley, and also this Tullamarine flow around 4.6 million years ago. The Tullamarine flow, which was the first of the larger volume flows in the Melbourne area, I wasn't able to find the source of that one, perhaps because it was buried under one of these eruption points or at one of the subsequent lava flows. But that actually interferes with the cross section over here. You can see it goes down this valley through the Bulla granodiorite. And yes, I was going to say something else, but I can't remember what it was. At 4 million years, we have the next couple of eruptions, Redstone Hill and Springs Hill. So Springs Hill doesn't interfere with our cross section here. Redstone Hill fills this valley over in the west. At 3.8 million years, we have Aitken Hill erupting, filling 2 valleys through the Bulla granodiorite. This is a bit of artistic license because this is actually not present at the moment, but I'm suggesting it might have eroded away. Our peak in activity was between 3.8 and 2.3 million years ago. We have 3 large volume eruptions from Fenton Hill, Tulloch Hill and Mount Cororoy. The Tulloch Hill flow is the largest flow in the Melbourne area. This was at 2.3 million years ago. You can see it filled up this whole eastern part of the Melbourne Valley. So a pretty large volume flow there. And the Tulloch Hill flow, sorry, the Fenton Hill flow also fills this narrow valley over in the west of the cross section. The most recent activity in the Melbourne area was from Mount Fraser at 800,000 years ago. And that again filled this valley that had been etched into the Tulloch Hill flow over in the east. And it made its way all the way from Mount Fraser, which is about 40 kilometers to the north of the CBD, all the way down to the CBD through here. So the longest lava flow in the Melbourne area as well. And since that time, it's just been a story of uplift and erosion, volcanic quiescence, so no volcanic activity, a bit of human activity to move around a couple of rivers artificially. But basically the story is that the surface of Melbourne is much younger than it was 8 million years ago. So a lot of the surface is covered by these lava flows, which are less than 5 million years old. And we don't have any of those really wide valleys that we had before all this volcanic activity began. So a much different surface to what we had to start with. So the main story is that before 3.1 million years ago, all the flows were pretty much, most of the flows were smaller volume, so they didn't change the surface of the Melbourne area too much. And since 3.1 million years, we've only had 4 lava flows, but they've all been pretty large volume. So those are the lava flows that have really changed the surface of the Melbourne area a lot, diverted rivers and stuff like that, and turned it into the Melbourne that we see today. The final point, the current period of quiescence, so the current period of no activity of 804,000 years is not the longest. So we have had a gap of 1.5 million years between the Tulloch Hill and Mount Fraser lava flows. So the fact that it's not the longest period of quiescence suggests that we can expect future activity at some stage. So yeah, there probably will be an eruption sometime in the future. So I'll leave you with that thought and pass you on to Michael Webster. He's going to talk a bit more about the general geology of Melbourne and how the geological mapping techniques have evolved over time.
Thank you very much, Michael. And can I just say I have in fact learned a few things from your talk as well. So thank you very much. That's much appreciated. All right, so Michael, just give me a shout if you can see this presentation.
Yep, I can see it.
Very good. All right, so as Mark has alluded to, this is the 1973 Geological Survey Victoria Melbourne map sheet. And this is still used widely as the geological map of note for the purposes of engineering. And in fact, a lot of my talk is going to be more in line with how we apply these maps and mapping techniques into the field of engineering. So my background, as you know, is both a geologist and an engineer, and my profession really does merge those two things together. All right, so what we see here is you get sort of a split, a bifurcation of the geology of central Melbourne. You get this big stripe of tertiary age material, which is 40 million years ago to about 2 or 3 million years ago, split with some older and younger stuff either side. And this is actually, it provides a very good window to see geology of different ages across Melbourne. You've got anything from stuff that's first deposited practically yesterday in geological terms through to things that are in fact quite old. And just as a little bit of reference, as we zoom into the Moonee Ponds Creek area, we're going to talk very briefly about that oldest of geologies around Melbourne, which is the Melbourne Formation, this grey unit here. So it's a Silurian age deposit, which puts it at about 420 million years. One of the best exposures that you can see when you are in fact allowed to leave your home again is along the Eastern Freeway. You get these beautiful exposures of rock. Now what you'll see there is this pattern. It almost looks like a little, it's bent. The rock. So in fact, when this material was deposited, it was laid down relatively flat. And then 420 million years, 430 million years, it's a long time. And so a lot of things can happen to it in that time. As Mark was alluding to, tectonic processes happen. And so this rock has been deformed since then. And those processes of deformation have a profound impact on the way that we engineer in that rock. And those deformations are recorded in the geological map itself. The next oldest unit on this map is in the Eocene. So we're talking, 40 odd million years ago here. So just to put that in perspective, we go from 420 million years. Yes, there are some granites around in the high 300 million years, but ultimately in this area, 400 million years to about 40. And just to put that in perspective, the dinosaurs came and went during that time, and there's no record of them in this area. It's a huge gap, and geological time is a very hard thing to grasp, but I hope you gain an appreciation through that. So as Michael Heath alluded to, the valley systems that we see today are very different to the valley systems that were around previously. And so what we see here, this little TE unit, and it just pokes out beneath another unit called TVO, the Older Volcanics Basalt. So what we have here is a big, broad valley system that's deposited a whole lot of sands and clays and in fact coal deposits too. And then that's been capped and protected by a basalt flow or a series of basalt flows. And as I hope Michael has also made you realize, labeling things as a single basalt flow is not necessarily the most accurate way to describe them. And the Older Volcanics Basalt, which is this brown unit that you see here, and I'll show you an example of that in a second, is a really good case in point for that. All right, so, sorry, I'll just jump ahead then. We have got Older Volcanics Basalt and Brighton Group formation here. Now, Mark was describing this around the Studley Park area. It's a very widespread unit. But again, it changes in its appearance and in its composition across Melbourne. And in fact, there are areas where you've got the Brighton Group formation, which has had a lot of iron in it, because in some parts it was marine deposit. And that iron has been leached out of the soil and then re-cemented in another area. Mark alluded to ironstone gravels. You can in fact have more than that. It can basically turn your soil into something with rock-like properties. And we find ourselves in a very interesting situation in the Royal Park railway cutting, where you've got a soil that looks like a rock and a rock that looks like a soil. So the Older Volcanics Basalt here is weathered away to this white powdery clay that you see down the bottom, and up near the top, the Brighton Group sediments, or soils, as they normally are, have got strength equivalent to concrete. It's geology's, it's varied and it's interesting, and it's quite tricky sometimes. And speaking of this Older Volcanics Basalt, and as Michael was alluding to, mapping these things as a single unit it helps us understand things, but it doesn't necessarily tell the whole picture. So everything you see here is part of the Older Volcanics Basalt as mapped. You have multiple flows. You've got a band of volcanic ash, I think we've inferred, that's devitrified into a clay. You can even have in amongst this other things depositing at the same time. So we've found examples of peat, so old swamp deposits underneath Footscray and places like that. So again, the map tells us the general unit, but it doesn't necessarily tell me exactly what we are going to be engineering in. Okay, so moving forwards into the Quaternary, late tertiary, early Quaternary, because I know Michael will correct me if I don't say that, yes, this is not just a Quaternary deposit, even though it is noted as such on the geological map. The Newer Volcanics Basalt is one of the most significant units to Melbourne. It's a lot of Western Melbourne's bedrock, so to speak. It's varied. There are multiple flows, there's multiple weathering, and I'm not going to go over it too much more because we have a guy with a PhD on the line at the moment on this, and I'm going to let him field the questions on this. However, it is a very tricky unit that does in fact bury things that you would otherwise note for engineering purposes. So it's flowed down valleys, particularly in the north and the east of Melbourne. So on the top right of that picture there, you can see around Collingwood and Abbotsford, for example, it's flowed down old river systems and it's buried the topography. So underneath these lava flows, you can sometimes find leaf beds, you can find peat bogs, you can find river gravels, or you can find no sediments at all, and it goes from basalt straight onto the Melbourne Formation. It's quite varied and it's quite unpredictable. All right, now we're going to focus in on this area. So what we have here is the Yarra Delta sequence. Now you can see on this map that it's just shown as one colour, because in this area of town, The most recent unit that you'll see is a unit called the Coode Island Silt. Now, most of the time, geologists tend to consider soil units an irritation, a distraction, because the bedrock geology is what it's all about. But the Yarra Delta sequence has had a lot happen to it. There are more than 10 units in where that star is there, and particularly if you think about its location, which is South Bank, that has it has a huge impact, as Mark was saying, on the way we engineer. And so one of the most common uses for these geological maps in Melbourne is for engineering firms to try and gain an understanding of what's happening in the ground as to how we are going to build sewers, build tunnels, build high-rise buildings. All of that rests on or in the ground, and it all comes back to these geological maps. It's always the first port of call. All right, so now zooming in on this area, I want everybody in their mind's eye to take themselves to Elizabeth Street, down by Flinders Street Station. If you stand there at the end of that tram stop and you look up the hill, it's kind of flat. Well, look up Elizabeth Street, it's kind of flat. Look east or west and you got little hills rising up. So Elizabeth Street was actually known as Williams Creek in the early days of European settlement. It is the main watercourse through Melbourne's CBD. And so as Mark alluded to, circa 1860, we get these beautiful geological quarter sheets produced by Selwyn and Co. But by that time, there was already a city built in the CBD. Now, by logic, you would think that the city would have, sorry, the creek would have river alluvium sitting beneath there, but there's none mapped. And see, and if you look at that white oval in the top corner, it says Melbourne Formation to the east of Elizabeth Street and basalt to the west. And then you head forward to 1937. And again, the new update to the geological map, it doesn't show anything. And we know from our investigation data through here that we've got 10, 12, 13 metres of sediments below here. So it's not like they prove that it's not there, it's just not noted. You go to 1959, again, not there. And then in 1974, we show what is known then as the Elizabeth Street Formation. Now, again, taking this into 3 dimensions, what we find is this. So you see the Elizabeth Street Formation there, that little green snake running up the middle of the map. And this is on a deformed topography. Now, Melbourne's geology isn't that steep. I've exaggerated that so we can show you the way that the landscape undulates. And what you'll note is that off to the right of that Elizabeth Street Formation, there's another valley. And again, there's no sediment noted there. The Elizabeth Street Formation ends before you get to the top of the valley. So it is a representation, but it's not necessarily the answer. And as Mark was saying, it is a hypothesis and it needs to be tested and refined over time. And in fact, to that end, there was another geological map published for Melbourne, the 1997 1 to 250,000 map. And it's a big one. The geological map spans a huge area. And this goes to scale. Scale is a really important thing in these maps. And so when we zoom in, and you can see, you know, in a clockwise direction here, we're zooming more and more in, you can see that little yellow, the yellow outcrop in the middle of that plan there on the bottom left. That is the inferred outcrop of that river or that creek alluvium. And so you can see they've captured that branch off to the east there. But because it's made up of a few dozen pixels, for the purposes of engineering, it doesn't really have that resolution that we need. And so the 1 to 63, 360, the 1973 geological map, 1 inch to 1 mile as it was known, is the one that's still most commonly used. And so this information isn't necessarily captured by a lot of people. And so referring to old maps it's very, very important. And I hope to really emphasize that to you now with this next slide. So here we've got the old course of the Yarra. I'm sure this will be news to some of you on this presentation, that the Yarra River wasn't always where it is now. So when Europeans arrived, the river actually was a long way north of where it is now. And we, over time, had straightened the course of that river to allow ships to allow ships in and to dock. And so what you'll see by 1937 is that the river has completely changed course, and they've noted where the old river channel went, that pale green line. Then by 1959, that's now, that the dashed line actually doesn't refer to that river course at all. That's a council boundary. It's got nothing to do with geology. It's just there as a hang up from when the river was in a different location. But if you were to refer to the 1959 map, you wouldn't know that an old river used to be there and it was filled in. And from an engineering point of view, that's critical because it can be 8 or 10 meters of very poor quality sediments. It could be contaminated, whatever it is. And that data is not captured. Come forward to 1974, it's back. You can see the old course of the Yarra. But then by 1997, it disappears again. And that's not saying that the 1997 map is wrong. It's merely saying that that is not a focus of that map. That 1997 geological map was very much a pure geological map, whereas the 1974 map was constructed more for development of the city, of engineering. And so you can see here how having an arsenal of maps behind you, it really shows you the way a city is developed, and it shows you that certain things are added or subtracted from maps as they go through time. And so you don't throw away an old map because you got a new one. All right, now mapping in 3 dimensions. So as Mark has said, we take these things into 3D. The top image there is when we bring in geophysical information into 3-dimensional space. So that's resistivity testing of the ground. And you can see its strong reaction to where that granite is, and then it drops away very quickly when the granite disappears. We use downhole geophysical techniques in the middle image here to show the way that the bedding of the Melbourne Formation, you know, those beautiful bands that you saw earlier, how they vary with depth down a hole or across an area. And that has a profound impact on the way that we construct any kind of basement or excavation, such as the current grade separations that are happening over Melbourne. It has a profound impact on the way we design them and a big impact on cost and safety. But my favourite image is actually the one on the bottom right. And this shows the bedding again in the Melbourne Formation, but this has purely been made through outcrop mapping. So you get a bunch of outcrop mapping. I think there are 200 or 300 points of data in this area. You put it onto your topography surface and you interpolate in 3 dimensions, and you get these beautiful interference patterns. You can see the way that the various geological events have shaped the bedding. And again, this is particularly critical if you wanted to put a tunnel through it or something of the like. Okay, now zooming into the Yarra Delta, as I believe I have a moment to speak, not very much though. I'll just quickly show you how we take this into 3 dimensions before we wrap it up and we talk. So just very quickly here, we have got here Melbourne City. So this is South Bank, as I was talking about before, and the Yarra Delta sediments through there. And I want to just quickly show to you if I can. Here we go. A cross section through a geological model. All right, so looks like we're struggling a little bit here due to limitations of zoom, but it looks like we're at this scale and we're going to have to stay with it. Okay, so what we've got here.
I can't see anything, Michael.
Oh, I do apologize. Thank you, Mr. Heath. I will attempt to share that screen again. New share. Okay. All right, Michael, how are we going now?
Yep, good, good.
Excellent. There we go. Okay, so very briefly, we've got ourselves, I'll reorient everybody. That is the Arts Centre. That's the spire of the Arts Centre. That's the Hamer Hall. That's Flinders Street Station. So we take a slice through this. What we find is that the subsurface geology, despite the outcrop information saying Coot Island silt, which is correct from here to here, the outcrop is Coot Island silt, but we've got a little bit more information than that. And we need to take this into 3D and understand these 3D relationships, map in 3D by drilling holes and pushing probes into the ground. And so when we're going to peel this off, what we can see is a whole series of old valleys and some of these lava flows that Michael had alluded to. So you've got, in fact, one lava flow here, and you've got another one buried much, much deeper in the ground, and I'll bring that up in a second. And you can see the way that these old valleys are influenced by what's happened previously. So we had a lava flow here, This is the most recent lava flow, 800,000 years, and it forced the river south, and it pushed it in a completely different direction through South Melbourne. And this is repeated time and time again in this three-dimensional model, that you get all these old valley systems. That's another lava flow in here, completely different age, completely different location in the profile. It's separated by probably 15 meters from the one above it. You get a dozen units through here, and they're all interacting with each other, and they and when you bring it into 3 dimensions, you can see those relationships that you can't necessarily see when it's just mapping. So I will jump back into the PowerPoint again. So please forgive me for one moment. Share screen. Science fair. Okay, there we go. So just to summarize the information, maps and mapping are essential to safe engineering design. You can't get away from them. They're so important. And it's not just maps, static maps, it's also going out and confirming when you're digging a basement, when you are out on site designing a tunnel. Mapping is essential. You always add to that hypothesis and refine it. Newer maps don't always mean better, they're just newer. And they may be there for a different purpose. So make sure you look at the old stuff too. Sometimes before a city was built on top of it. And mapping and organizing information in 3D helps better understand the ground and reduce the risk. So if you don't know what you're investigating, it's unlikely you're going to find anything of use, and you're going to open yourself up to all kinds of risks. So know what you're getting into, bring that information into a point where you can really interrogate it, understand it, and refine those hypotheses that were done by the shoulders of giants, as Mark would say. And yeah, that's what we do. And we will continue to do that and refine those processes over time. And I'll pass now back to Mark.
Great. Well, thank you very much, Michaels. That was fantastic. I want to conclude with just another broad overview. So geological mapping really benefits from diverse approaches. It benefits from thinking about things at a variety of different scales. It benefits from heritage knowledge, different perspectives and different knowledge bases carried through time. And I just wanted to show you some of the places around the world where I've had the pleasure of being able to make geological maps. Geological maps at a continental scale in the Canadian Arctic, in Baffin Island, and on the Canadian Shield as an undergraduate student. As a master's student, I got to make geological maps in the Grand Canyon and in Mexico of the southwestern United States. Mexico and the southwestern United States. I was able to, as a PhD student, make maps of Atoro Island in East Timor, as well as maps in Central Australia, in the Himalayas, and trying to understand mountain growth. I've been able to make geological maps in East Africa, in Iran, for understanding the relationships between humans and their environments, and of course many maps of the geology in New Zealand, including a map of my own backyard, which liquefied 10 different times during the Canterbury earthquake sequence. And so from all this geological mapping, it's given us such a diverse and interesting view of the world. It's helped us both understand the way that Earth works, but also our connections to landscapes and cultures. And ultimately, it allows us to contribute to informing decisions for a more sustainable future Earth in a variety of ways. So thank you very much. I'm going to sign off now. We appreciate your audience, and all the best through the continued lockdown.
Thank you so much, Mark. And to Michael and Michael as well, as you all just come back in. That was fascinating. I don't know, well, actually, I probably should quote Catherine Horsfall, who in the Q&A has said mind blown, because I'm quite similar. I think I was about this close to my, my screen for the majority of that, checking out all those maps. Fascinating talks. Thank you so much. Really, really interesting. We've got probably about 5 minutes, which is just enough to probably have a couple of questions, which is great. And I'm sure the audience would really love to hear a little bit more from you all. So I thought we might start from, I guess, some sort of foundational stuff from Maddie. Maybe I'll throw this one to you, Mark. So what is the general geological process for classifying different types of material, i.e. sediment and rock?
Was it to Mark or to Michael Webster?
Oh, sorry, Mark. I have to be very clear, Mark. I should just call you by Quigley.
Yes. Well, we use when we go into the field and we identify different rocks, we rely on a classical principle way of describing the structure and the texture and the composition of those materials. We use hand lenses. We use a variety of different geological tools. We make notes in our field book. We have a variety of classification schemes, geochemical, grain size, observational, and so from that basis we progress. Now, I think one of the things that comes up often is differences in nomenclature. Engineers like to call things soil. Geologists like to call things sediment. But we do describe soils as well, but we tend to think of unconsolidated sediments. We call them as such, whereas a lot of engineers call them soils. So there's nomenclature changes and things that happen that we have to address. But the principles upon which we use have not changed all that much through geological time, and so we still rely on those bases.
Fantastic. Okay, great. Thank you, Mark. Now, moving on to volcanic activity. So, Michael Heath, I think you could have expected some sort of question if you finish a presentation on there's a potential for volcanic activity in the future. So I think there's a few questions about this, Maddie and Callum. So what do you know about when the new volcanic province next erupts? And what initiatives are in place to detect and respond to future volcanic activity in the Melbourne area?
Okay, what initiatives are in place? That's a good question. Not a lot. It's not considered a major risk to people's lives or livelihood at the moment. Basically, if we were to have an eruption in the future, most of the youngest activity is a long way to the west of Melbourne, and yeah, to the kind of south and southwest and west. So we would probably expect any new eruptions to be possibly in South Australia or in Western Victoria. And it is possible that they could be more phreatic magmatic type eruptions because there are large aquifers out there. So when
what's a phreatic magmatic eruption?
So a more explosive eruption because there's water in the ground. So when you have water in the ground, you get the lava interacting with water before it gets to the surface, and then it basically blows up under the ground. So that's how you get big holes in the ground rather than nice peaceful lava flows. But luckily there aren't too many people out in Western Vic and Eastern South Australia. So hopefully it doesn't blow up someone's house. If we were to have an eruption in Melbourne, it would be more likely to be the nice peaceful lava flow type. But you could still expect a volcanic edifice of 50 meters or so high. So you wouldn't want to have your house there either. But yeah, not too many people affected, or other than a lot of people being evacuated. Obviously, they move rivers around and that kind of thing. But it would all happen fairly slowly, I think.
Okay, sure. And no idea about timeframes, or I was hoping the answer would be that's not going to happen until the distant future.
In the Melbourne area? It's overdue, so yeah, but okay. Whenever, yeah, any time now, yeah.
Hopefully okay. This one as opposed to Yellowstone, though.
I'll become super relevant. I'll become super relevant if it happens, so I have my fingers crossed.
Okay, okay, moving right along. Okay, so we've really only got a couple of minutes. So one last question from Catherine Horsfall. So we'll throw this one to Michael Webster. Re-quoting her, mind blown, loved it. Can you recommend any way to start to better understand Melbourne geology, or do we have to wait for Michael Heath publishes his comprehensive book, or possibly you might be starting your own books as well? I don't know. But yes, any recommendations for where we can find out more?
Okay, so yes, there's a really good publication that you can get from the Melbourne University Library. It's called The Engineering Geology of Melbourne. It's referred to as the Blue Book. And that was published in about 1992 from memory. So not everything in that is exactly as per, but it's a really good basis. It talks about a lot of old engineering projects, things like, they even quote things like when they were drilling a tunnel down in the southeast, so around Cheltenham, they come across a unit called the Finesford Formation. And they go into detail talking about how the Finesford Formation's got minerals in that actually absorb oxygen, as they had a couple of miners asphyxiate inside that tunnel back in the day. So there's quite a lot of history in that book too, a lot of lessons to be learned from that. So talk about that. They talk about the excavation of the rail loop. They talk about the Westgate Freeway. So there's a lot of interesting geology in there, and that's a really good point to talk about. But I'd also throw this to Mr. Quigley. There we go. Oh, thank you very much. Dr. Quigley, I should say. There's a lot of publications out there as well. The GSV, Melbourne Uni, Monash Uni, they've all been doing fantastic work, and they really need to have that credit for that. A book published in 1992 does not have, you omit nearly 30 years of research since then, so you definitely need to refer to those publications. It's a great foundational textbook, gives a really nice overview, but to go from there, you start with that, and then you can keep reading the more recent publications.
Just popped a bunch of stuff in the chat. There's a bunch of links there. We've just finished making a little micro documentary, visiting a lot of Melbourne's geological sites that you can look up on YouTube. But of course, a Google Scholar search of Melbourne's geology will lead you down the avenues of the scientific literature. There's a tremendous amount of awesome material on the Geological Society of Victoria and Geoscience Australia websites. So there's no shortage of things to keep you busy.
Fantastic. Okay, so unfortunately we are out of time, so we might wrap up there. But Mark Quigley, Michael Webster, Michael Heath, thank you so much. It was a fascinating talk. Clearly everyone is really interested and no doubt going to be off finding out more. I'm definitely going to be looking at Melbourne in a very different way, and letting everyone know that the Yarraroo was not originally where it is right now. And I'm going to start calling Elizabeth Street William Creek. So you've definitely changed the way I see things. So thank you very much. It's been fascinating. Thank you to the audience for zooming in to this mid-afternoon masterclass and all week. I hope that was really, really enjoyable, and have a fantastic weekend. Happy National Science Week.